Welcome back, geologists, and we'll be talking about sea level changes and Sloss sequences today, along with some unconformity review. So you're looking at a black sand beach, which is right near South Point of Hawaii, and you're looking at the current sea level. Well, I can tell you even in Hawaii, sea level change is documented. But worldwide, we have 6 distinctive sea level sequences where sea level rises and then falls globally. So we're going to look at those and take it a step further from what you learned in physical, because this is a foundation that's a theme throughout all of the Phanerozoic eon. We need to have a review of unconformities just so you recognize how they fit into the Sloss sequences, and we'll get to them shortly, the Sloss, but let's start with a review of unconformities. An unconformity is a gap or a hiatus in the rock record. Simply stated, we're missing some of the rock record. That could be from one of two things. Either we had a period of non-deposition, which can occur, or that rock was deposited and it was eroded from the rock record. You might be wondering, how do we know that it has been eroded? Because we can find it nearby, the same rock layer, same age. It's just not in the area that we're looking. We can also look for other clues, such as sequences of rocks that should be there if we had a sea level rise during that time or a sea level fall. Because rocks get laid down in a lateral and vertical fashion once you get a series of sea level rises and falls. So when you have a contact between lower rocks that are older and ones that sitting on top are younger, and there's something missing in between, that is an unconformity. This is a classic angular unconformity. This is in Cody, Wyoming. Can you see the angled sedimentary beds here? So some kind of deformation occurred that uplifted those to this angle, or in the case that you're looking at, more like this. And then you get flat ones that came in overlaying right here. The rock types are dramatically different. This is a sandstone and then a very interesting conglomerate layer. Notice that it's not a nice straight line. Can you see it's wavy line? Well, that's why geologists draw unconformities typically one of two ways, with a red straight line in a block diagram, or they'll actually draw in a wavy line, because that's typically what it looks like in the rock record. So in an angular unconformity, the bottom older layers are tilted and the younger ones are flat on top of the unconformable contact. A disconformity is where you're missing some rock record, but you got all horizontal rock layers. So it'd be like a deck of brand new cards and you're missing some in the middle. Or you buy a book and you're missing 5 chapters somewhere in the middle. These are sedimentary layers above and below. So here these layers are in sequential order. But do you see how the rock texture changes right about here? We're missing some gap of time right there. And so that is an unconformity. And it's called a disconformity. I like to nickname it the disappearing act of the parallel sedimentary rock layers in the middle. So you might wonder, how can you really figure this out? You usually need to look for fossils. This is where the law of fossil succession becomes very important, because we can look at sequences of fossils to tell if we're missing something in between. A nonconformity is where you've got an igneous or metamorphic rock formation at the bottom, overlain by flat, newer sedimentary rocks between them and the unconformable contact. In other words, all this stuff in the Grand Canyon's Precambrian, and directly above it, we've got Cambrian age rocks. We're going, well, that's in sequence, Precambrian to Cambrian. Not so quick to judge that, because the gap between this right here, this unconformable contact, is 1.2 billion, with a B, billion years of missing time. So you can be walking on the Bright Angel Trail and actually walk over one step and have lost that much geologic time. There's a story there. So nonconformities tend to, not always, but tend to most of the time, represent huge, vast quantities of erosion or non-deposition. So we need to have a quick review of marine facies, which are transgressions and regressions, in order to talk about Sloss sequences. So sedimentary rocks are deposited at the same time in different places in the ocean. So you got some at the coastline, meaning the shoreline. You got some right out on the near shore. You get lagoonal rocks, and you get wide open sea rocks that form. Each depositional environment, the further away you get from the coastline, becomes less energetic, and subsequently the sediments get smaller because the energy is so much calmer. So the closer you are to shore, the bigger, coarser the sediments are, like sands, and then you get farther away, they turn into muds and limestones. And also, the further away you get from the coastline, the less terrigenous input they have, which means the less detrital material from continents washing off from rivers and snow melt and rainwater. So what happens is rocks will have a different characteristic look based on where they fit into the shoreline, the near shore, lagoons, and then open ocean. And you can see different rocks form in different environments, like sandstone forms in a very high energetic shoreline surf environment. So that's why you have bigger grains. Silt is near shore, and that has moderate energy. It's a little bit smaller grain than sandstone, if you recall from physical. Shale is lagoons, and those are going to be lower energy rocks, so you're going to start to make a finer grained settling out. It's like comparing sugar to Splenda. And then far away from any terrigenous input, you can hardly make anything but a carbonate rock known as limestone. So this is a place in Waco, Texas called Lover's Leap, and interestingly enough, this section right here has completely mass wasted off. And you have a big rock slide there now, so you can really see very well the different layers of limestone. And so I like this image very well because it looks like it's stair-stepping. So in between each one of these stair steps of limestone is a softer rock known as shale. So the limestone is farther away from the coastline. So if I have limestone on a continent, that means the water was either deeper or further away from the coastline in the right conditions to make limestone. But if I have shale, it means it's a little shallower water, and it was closer to the terrigenous input because it's still making detrital shale rock. So in the case of Lover's Leap, we have alternating layers of limestone, shale, limestone, shale, limestone, shale, limestone, shale. We have over 20 sequences of that, indicating during the Cretaceous period that sea level has been rising and falling with enough difference to change X marks the spot at Lover's Leap to be a different depositional environment, thus creating a different rock type. So a transgression by definition is a rise in sea level. And this is where exposed parts of the craton or the continent are now covered with an ocean. However, they may not stay that way indefinitely. What are causes of transgression? Well, they are caused by increased activity of mid-oceanic ridges, which actually causes mountains to grow at the bottom of the ocean and spill that water onto continents. Another thing that could happen is we have a melting of a major set of ice polar caps. And then, of course, we could have coastal subsidence, which is something that happens even today in places like New Orleans, where they're pumping groundwater faster than it can be recharged, and it's causing land subsidence. So the image of the Great Barrier Reef today is what I'd like you to imagine wherever you're living on a continent, and think about that being the environment of a shallow sea that covered areas at certain points of geologic past. A regression is where sea level drops. So areas that were covered by the ocean are now exposed. And when that happens, as they become exposed terrestrial land, habitats can move. And so this is just a construction site, but this is kind of the image I'm wanting you to have, is the land's now vulnerable to erosion. So during a regression, we erase what has been laid down during a transgression. Maybe not all of it, but the stuff that wasn't covered by an ocean very long doesn't have much thickness of sediment deposition. So it stands a higher probability of being erased than the edges of the continent, which have a longer duration of being covered by that ocean. So what are causes of regressions? You have a very inactive time of mid-oceanic ridges, so the mountains aren't as deep, so the water kind of spills back into the ocean off the continents. Second is you can create an ice age, which will suck up water. and lower sea level. And third but not least, you have localized uplift of mountains. So let's say you get a mobile belt, and that mobile belt ends up having uplift that can divert the direction of water and actually change an area from getting covered by water. So marine facies is the end result as sea level changes. The rock layers that represent, like in Lover's Leap case, limestone represents far away from a terrigenous input. The shale represents lagoon. Limestone far away from a terrigenous input. A shale layer in between represents a lagoon. So they get stacked one on top of the other, as you see here, as vertical rock layers, telling a story. So while this particular site may tell the story of lagoons and far away from terrigenous input, if we went further into the continent for this same time period during the Cretaceous period, we could find the shoreline and nearshore rocks that do the same thing. And so we're left with a vertical sequence of rocks from the lateral deposition, all that happens at the same time, from the shoreline, near shore, lagoons, and far away from a terrigenous input. You do that and change sea level enough, you're going to end up with a storyboard stacked one on top of the other that tells the history of an area geologically. So if I see a diagram like this where limestone's at the top, and you recall from your physical days that all blocks are limestones, dashes are shale, dash dot is siltstone, and all dots is sandstone. So I would say if I saw this, that means that we had a transgression most recently. If I see sand at the top, that's the youngest rock layer. Remember Steno's law of superposition. Then I would know a beach was the most recent depositional environment. So what does that equate to when you're looking laterally? So you can see sea level 1, 2, and 3 here. And do you see how these jags are going? Let me follow one, and we'll be looking in this section right in here. Small transgression, small regression. Small transgression, medium regression. Large transgression, small regression. Large transgression, big regression. Small transgression, large regression. And you can see that everything moves laterally this way in a transgression, back this direction towards the ocean during a regression. So we're left behind with what Walther's law says, which is vertical and horizontal rock layers that tell a story. And the Lover's Leap area, we were looking at this profile right here. So don't mistake the stair steps that you saw with the pictures of the limestone at Lover's Leap with this right here. It is the same thing, but the stair steps are not caused because of transgressions and regressions. They're caused because of differential weathering. So the limestone's more durable. It has a lower differential weathering capacity as compared to the shale with the high differential weathering capacity. All right, a couple of things that you're going to need to know that you may not have ever seen before. Some words that are common in your textbook in any historical class is the word called cratons. Cratons are the oldest and most stable parts of a continent landmass, meaning they've experienced very, very little deformation from being squashed or ripped it apart, either from plate collisions or divergent plate situations. Shields are the basement rock that crops out at the surface, and it's Precambrian in age. So anytime we've got shield rock, it's the oldest, and sometimes if you're looking at really old shield rock, it is some of the original stuff that we got made during the Archean. Platform represents all the basement rock that's been overlain by newer rocks, sedimentary layers for the most part. Sometimes you'll get igneous lava flows, those kinds of rocks on top. But these would be things like your shields and platforms. Looking at your diagram down there, you can see that the red is the shield and the pink is platform. So this is all the rocks that have covered or that are covering our shield rocks. And this is exposed shield rock. And all of this stuff over here are going to be additional platform rocks that have been added on when we get mountain building events. So the long story made short is every continent has some roots or some interior sections that are the original continental masses, and then all the edges are typically add-ons. And that's another theme of this course. So mobile belts, I mentioned that word earlier, those are regions along the perimeters or margins of a continent, like the Cordilleran Belt here, the Ouachitas from down south, and then on the east side of North America, we have the Appalachian Mobile Belt. You're going to need to know what all three of those are and which part of the continent they represent. There'll be themes that come up regularly in every geologic period when we get to the Phanerozoic, because we have mountain building episodes that have occurred in which we have evidence of that mountain building, even though the mountains may be gone. Another term you're going to need to know is something called an epeiric sea. The image of the Great Barrier Reef again illustrates what an epeiric sea would look like. Imagine this is right over the area where you live right now. These are shallow marine seas that cover portions of continents, and they provide super fabulous, fantastic, excellent habitat for marine organisms that like shallow marine environments. So I do need to define a little bit about shallow. So most of us, the shallow end of the pool is what we define as shallow. That could be untrue in geology. You can have shallow being just a couple of feet of water to being about 700 or 800 feet of water. But I think shallow really needs to be determined by, is it a depth in which life forms could exist, where a majority of your life forms would be. So that makes the kind of the definition for geologists. So when an epeiric sea falls off the continent during a regression, this leaves marine habitat completely barren, and those poor animals run and hide if they don't move back with the water fast enough, and they die. So that's how we end up getting extinctions when sea level rises and falls occur. Crotonic sequences is simply a big word for a rise and fall sequence of sea level, so a transgression and regression sequence. When you have a transgression, you'll have increased periods of deposition. That almost seems backwards, doesn't it? But keep in mind that sediments and animals can get buried in those sediments fairly quickly in an oceanic environment, unlike you will on land where it's harder to get buried. So transgressions will allow for huger quantities of materials to get buried and deposited. So you should see a more extensive rock record from a transgression than you would a regression, simply because the continents get covered and you have a chance during the ocean coverage to deposit more sediments. So even though these are stromatolites and tidal flats, they're going to likely get preserved in Shark Bay, Australia as fossils down the line because they're covered by water most of the time. And as sea level rises on the continent, I would almost guarantee you that they would get buried. However, if we have a regression, these things are going to get exposed and they might get eroded away. During a regression, you should see major unconformities occur, and this is because the land's exposed and can have different depositional environments, like you see here in Glacier National Park, erase part of the rock record. So in the field, we look for these major unconformities to determine if we are seeing a change in the cycle of transgression and regression. They've been mapped out by a gentleman by the name of Lawrence Sloss, and we'll get to him in just a minute. So let's talk about, with that in mind, I want to visit why we have so much more sediment on the edges of the continent in terms of rock record from transgressive regressive cycles than we do from the center. As sea level works its way in, it's going to cover the middle of the craton for a shorter length of time than it will as it even transgresses and regresses off the edges. So the edges or the margins of the continent have thicker sequences of these rocks and tend not to have as many unconformities as the middle of the continent or craton will.